Welcome to VOLTTRON office hours. Today, we are going to kick off the meeting with a presentation by Aditya Ashok, who is a researcher at PNNL, talking about a very interesting research project that he's been a part of. If there are any, feel free to ask any questions. If you'd like to arrange some follow-up after the call, let Aditya or myself know, and we can arrange it. And these slides are cleared, correct, Aditya? So could you share the slides with people who are interested after? Are you there, Aditya?
Sorry, I was on mute.
No worries.
Yeah, the slides are cleared and should be good to share.
Okay, great. Well, with that, I will turn it over to you.
Okay, just a quick check. Are you able to see my screen right now?
Yes.
Okay, great. So let's get started here. Thank you so much, Jeremy. My name is Aditya Ashok again. I am a research engineer at the Pacific Northwest National Lab. I work in the Electricity Infrastructure Group. And today I'm going to be talking about our use of VOLTTRON in our project that is titled Proactive Adaptive Cybersecurity for Control Systems. We're using VOLTTRON in our testbed, and the presentation today is going to talk about co-simulation architecture that's leveraging VOLTTRON and Phoenix. So just a little bit of background about the initiative. The Pacific Initiative, which is the Proactive Adaptive Cybersecurity for Control Systems Initiative, focuses mainly on developing new technologies that are adaptive and proactive, as the name suggests, in the operational technology space, looking at industrial control systems or OT from a broad sense. A lot of the current technologies are static and are being targeted. So there's a strong need for developing newer capabilities in that space. We are looking at it from different levels. One is looking at the design process and then incorporating security into the design. And then the second one is developing new technologies that are adaptive and proactive. And these will actually include different aspects. They'll include the cyber communication, the physics of the system, and human behaviors together. And we hope that this actually creates demonstrably secure systems and increases the security and reliability of industrial control systems in general. So the testbed that we have is actually an environment where we are modeling two critical infrastructure domains. We're taking the grid and we're taking buildings, and we're modeling these systems in our testbed. So this testbed actually involves grid, buildings, a little bit of process control with the hardware that we have. For realizing this, we have a bunch of real-time simulators and simulation tools. We have the OPLRT, which is a real-time simulator that can model systems such as the power grid. We have Dymola, that is a generic tool that allows you to model different types of systems. In our case, we use Dymola to model the building. So the thermal characteristics of a building, including some aspects such as air handling units, VAV boxes, and so on. We have GridLab-D. GridLab-D is a distribution system simulator developed at PNNL. This is also used for modeling the electrical side of distribution systems and houses and buildings. VOLTTRON, everybody knows VOLTTRON is a platform for supporting data exchange between devices and simulation tools. We also use Phoenix, which is a co-simulation platform developed at PNNL, which is used for setting up network co-simulation experiments where you can connect different simulators, and Phoenix orchestrates these core simulations. We have a bunch of hardware and software. So we have relays from our Schweitzer Engineering Labs, specific relays. We have OPC servers, and we also have field controllers on the buildings domain. So we have Allen Bradley Control Logics PLC, which we are using to model air handling unit controllers. We have Johnson Controls network automation engine, which is typically used in the buildings domain as a supervisory controller. We have Wonderware to visualize and serve as our human-machine interface. We're using different types of protocols in the testbed. We have DNP3, Modbus, and BACnet. So basically, in this testbed, we have high fidelity power grid simulation, which is coupled to two different types of building simulations. One is just the electrical model of the building in GridLab-D, and the other one is a high fidelity commercial system model, building system model in Dymola. And the link between these systems are enabled through the use of VOLTTRON and Phoenix to sort of exchange information back and forth between these different simulation tools. So this slide shows a conceptual architecture of the testbed that we have put together. And this is a testbed that actually leverages heavily existing infrastructure developed at PNNL. Specifically uses a lot of the PowerNet testbed and also a lot of the infrastructure developed under an initiative called the Control of Complex Systems. In the testbed that we have for Pacific, we have the following architecture. And if we start out at the bottom right, the distribution grid is modeled within the OPAL-RT simulator. And this simulator is actually feeding analog signals to relays as they would be connected in a real field deployment. They get the signals and then they send telemetry information out to an OPC server, which is, let's say, which is acting as the control center where the operators are getting the telemetry and visualizing them in the HMI. So we're using Wonderware there. And this communication is happening over DNP3. And because we only have a subset of devices modeled for the rest of the network, we directly pull in the information via DNP3 from the OPAL-RT simulator directly to the OPC server. And this distribution system that we modeled in the OPAL-RT is getting information from different types of building systems which are acting as loads on this electrical system that we are modeling. And so these buildings are modeled in GridLab-D and Dymola, as I mentioned before. And in order to get the information back and forth, we are using the Phoenix platform, and we are using API that is designed to interact in real time with the OPAL-RT simulator. And as I mentioned before, VOLTTRON is serving two key roles here. One is to help the high fidelity Dymola building simulation send information out to the distribution grid simulation happening in the OPAL-RT. And the other is to interact with building devices in the testbed. So in that sense, we have an Allen Bradley PLC and several soft PLCs, which are just virtual devices that we have spun up. And these are intended to mimic, let's say, the air handling unit controllers that are deployed in a typical building control system. So VOLTTRON is used to communicate information such as measurements to these PLCs, and we use different protocols. So we use Modbus to talk to our Allen Bradley PLC, and then we use BACnet to communicate with our virtual PLCs or soft PLCs. And from there, the data goes up to a supervisory controller, which is our Johnson Controls NAE. And from there, the data is pulled into our OPC server via BACnet again. And then that data is also visualized at the HMI in Wonderware. And basically, if we look at it in a little more specific sense, the distribution system that we are modeling in the OPAL-RT is a microgrid. And for this microgrid, we have used a standard IEEE system model, which is the IEEE 37 node system. And there are different loads at different points in the microgrid, and several of these loads are modeled within GridLabD. These GridLabD simulations are interacting in real time with the simulation that's running in the OPAL-RT via the Phoenix framework. And then, like I said before, we have a high fidelity building model that includes air handling units, VAV boxes, and the thermal characteristics of the building modeled in Dymola. And that is exchanging information with the microgrid model via VOLTTRON and Phoenix. So if we look at the SCADA side of things, the control and communication, like I mentioned before, we have a Schweitzer 451 and 751 relay modeling relays that are deployed on the distribution system. These are getting their signals from the OPAL-RT directly via the analog and digital interfaces, and they communicate their measurements to the OPC server over DNP3. Similarly, on the building side, VOLTTRON is getting the information from the building simulators, namely Dymola and GridLabD. And from there, VOLTTRON uses the protocol drivers that are available to send that information out to the Allen Bradley PLC and the soft PLCs that we are using, which in turn send the information over to the Johnson Controls NAE, and then leading all the way up to the OPC server. So if we take a closer look at what VOLTTRON does in this platform, basically in the co-simulation, like I mentioned before, the buildings are loads on the microgrid. So for every few seconds, VOLTTRON is enabling the exchange of data from the Dymola building simulation, and Phoenix is enabling the exchange from the GridLabD simulation to the OPAL-RT. Specifically, if we look at VOLTTRON, we have developed a specific agent that does the following things. So in the beginning, that particular agent becomes a part of the co-simulation running under Phoenix. So as I mentioned before, Phoenix is a framework for co-simulation. So Phoenix has a broker that orchestrates the flow of simulation time. So different simulators join Phoenix as federates, and each simulator publishes information that is needed for the other simulators, and then it subscribes to a specific subset of information, and it works via this publish subscribe mechanism. So in our case, the VOLTTRON agent connects to Phoenix and then waits for the other simulators, and when all the other simulators have joined, it also initializes a connection with the building simulation over a socket connection. So in our case, the connection between VOLTTRON and Dymola is over the socket connection. And once the initialization is done, the agent that we have goes into a loop, and it does the following things. So it constantly looks for messages that it has subscribed to from Phoenix. In our case, for the Dymola building simulation, it is constantly looking for the voltage on the point where the building is connected. And if it receives that measurement, it is going to communicate that information to Dymola. And then similarly, it also does the same thing for information from Dymola back to the microgrid simulation. And then it also does a process where it is writing measurements out to the field devices. So it is going to write values to the Allen Bradley PLC. It is also going to write values to the soft PLCs. And then it also reads values from Phoenix for the data points that are coming from GridLab D. And it does the same thing where it is writing those points out to the field devices via the BACnet or Modbus, and then it continuously repeats this process throughout the duration of the co-simulation. So that is what I have. I'll be happy to answer questions. I know it sort of went through quickly, but I'll be happy to pause and explain things that people have questions about in a more detailed manner.
Could you talk about maybe an example experiment you've run on the test bed?
Sure. So basically, if we go back, so let me go back to this setup. So I talked about the fact that we have a microgrid, and then we have different buildings and different buildings modeled in GridLab D and Dymola. So we have this setup for a use case, for a cybersecurity type of use case. So the use case is such that we have a microgrid that a particular organization has, right? And this microgrid is connected to the rest of the distribution system, and then it has its own backup generation source. And then as part of the microgrid, we have these different buildings that are spread out throughout the campus, including, let's say, a large commercial building that is doing some sort of a process control, or it could be a data center or so on. So the different buildings that are spread out throughout the campus, we modeled in GridLab D. And then the large commercial building that is looking like a data center or an industrial control system facility, we modeled that in Dymola. And then we have different building controls modeled using a combination of the Allen Bradley PLC and soft PLCs. And for this large building, we specifically modeled air handling unit controllers in these different physical controllers. And this system is, let's say, initially connected to the grid, and we do experiments where what if somebody does cyber attacks on this organization, right? So some employee gets a phishing email, he opens a malicious attachment that gives attackers access to the building substation, to the campus substation, and they are able to isolate this campus from the rest of the grid. And then if they are also attacking the buildings on the network, if they are targeting the air handling unit controllers to turn off these air handling units, what happens on the microgrid and what happens to the building controls. So this is sort of one of the experiments that we have run, and we are collecting information on, and we have different security technologies developed as a part of this specific initiative that will be deployed in this sort of a use case scenario, and then we demonstrate how effective the technologies that we developed are. So we are using VOLTTRON as a central glue here that is not only helping co-simulation, but it is also helping interacting with the real field devices and sort of creating a realistic environment that has a combination of simulation and real devices.
Great, thank you. Any other questions? I guess I have another one.
Sure.
What's the, I guess if people were interested in doing something like this, what's the availability of Pacific?
So in terms of external researchers using the testbed, so like I said before, this infrastructure is heavily leveraging the PowerNet testbed capability. So if external researchers were interested in using the testbed, we definitely have a way to work with people. In terms of usage, it is going to be sharing the usage of the simulators and the real physical devices that are being used. So that would be one of the things that might have to be worked out in terms of scheduling and the type of the system that needs to be modeled. So if they have a different system model that they have already created in OpenRT, then we can implement that. Otherwise, model development from that sense will be there. And then also in terms of the type of campus, right? So this testbed is not only giving you the option to design your grid system or building subsystems, but you can also design your own network, right? So you can design your organization to be of a specific type, and that will require a specific type of configuration on the testbed for the networking and the computational infrastructure in terms of virtual machines that are needed and so on. But definitely PowerNet is something that we want external people to look at and use. And the hope is that we have a set of models that people can start with, but then the goal is for people to implement their own systems working with us from that perspective.
Okay, great. Thanks.
Yep.
All right. Any questions or comments from anybody in the on the call? All right. If not, feel free to follow up over email with. You can email volttron@pnnl.gov, or do you have your contact information on here? Did you?
I forgot to add them. But so it is my first name dot last name at pnnl.gov. So that's ADITYA.ASHOK@pnnl.gov.
All right, great, thanks.
Thank you.
All right, for the next couple topics, I will turn it over to Craig to talk about the recent RabbitMQ merge into develop and then some Python 2 to 3 news.
Yeah, well, so we have officially merged in to develop the RabbitMQ branch. Posted that up on Slack yesterday, I think. Yesterday or the day before. So things are moving in that front. And so now I've shifted a little bit towards the 2 to 3 migration. I took what Kyle and James had and Elise had done and started merging it yesterday and finished merging it yesterday. And now I'm back to fixing some of the issues that have cropped up with the merge. So that's where I'm at. I hope to have laid out a better understanding of all the things that are now broken because of this merge on Monday or Tuesday of next week. So that's where we're at this point. And at that point, I think it would be good to have specific things that need to be done to finish off the merge, and I'll be putting those out on the Slack channel in the 3.6, or as I like to call it, 3.6 plus channel, because I don't think that it needs to be tied directly to 3.6, even though that's what the base distributions come with nowadays. So that is where we're at. Any questions?
All right. If not, yeah, you can use Slack to keep up to date, and if you want to get involved, just let us know on that. All right. Any other topics or questions or research that people wanted to bring up on the call? All right. Okay. Well, if there's no other topics people want to cover, then just remind folks that the VOLTTRON users meeting is August 29th and 30th here in Richland. As soon as we get the website set up, I'll send out a blast to the mailing list. For future VOLTTRON office hours calls, if you have research that you want to present, please let us know. We really like seeing applications presented here. It gives a chance for the development team to see how people are using it, and it gives more importantly, it gives the community a chance to see what others are doing and opens up paths for potential collaboration. So with that, I will call it a meeting. Thanks, everybody.